go on with another example. Maybe it'll be clearer then. Okay, let's say we choose say G, a map G from R to C to R3C, given by G takes X, Y, 2, um, let's try X plus Y and Y and X. Okay, well, this is going to be, it's going to turn out to be a linear map. And let's see, is this one-to-one? Well, what we do is we would take this form here, the image form, and say with two different vectors, we'd start from x1 plus y1, y1, oh, there's no z. What am I doing here? There's only an x and a y. Let's do this, say, x minus y. So we have x1 plus y1, y1, we have x1 minus y1. That's the image of the one vector. Then we have x2 plus y2, y2, x2 minus y2. Okay, so we say suppose that the images of arbitrary vectors x1, y1, z, x1 and y1, and x2 and y2. I keep remembering the previous example. We only have two components here, so x and y. Okay, so now what we need to do is we need to show x1 equals x2 and y1 equals y2, or find counterexample, The last previous one, we found a counterexample, a case when they weren't one-to-one. Well, here, this equation here gives you the three equations. X1 plus y1 equals x2 plus y2. And the second equation is y1 equals y2, and x1 minus y1 equals x2 minus y2. Well, the second equation here right away is just y1 equals y2. Now, if y1 equals y2, then the first equation, I can cancel off the y1 and y2 because they're the same, and this is going to give you x1 equals x2. So this, therefore, this map is one-to-one. So we have to suppose that the images are the same, then discover. Now here, you can, this is a linear system, but it's such a simple linear system in terms of seeing that we don't have to really, we can just sort of eyeball it and see that it produces the result that we want to show. Okay. That is, let's see. Yes. Okay. Well, what does it mean to be that's checking that a map is one-to-one. Now, it turns out that we're going to find simpler ways. This is sort of the way of verifying the map is one-to-one directly from the definition. And you can see it's a little bit tedious because you have to sort of generate all these variables. And we're going to find that we are going to be able to determine whether a map is one-to-one in a much easier way once we develop some other ideas about linear map, what's happening with linear maps. And so, but this is sort of the goal first of all. And so we want to also look now, let me make sure. Yes, okay. We want to look at the second property of being onto. And what onto means, well, let's deal, this was G up here. Let's deal first with F. Is F onto that map? What is F? F was the map X, Y, Z to X plus Y, Z plus Y. No, yeah, that's right. No, well, I didn't phrase it. It's X plus Y, Y plus Z. That's the same thing, but okay. So what is it? What it says? It says for any, so we have to choose any X, Y, and Z. That is, choose um, any um, vector, say P and Q, that's a member of R2C, and find the vector that it comes from, and find a vector that it comes from. And you can see here that so we have to be able to choose any vector here and then say, does this come from some vector here? So we have to do is we have to say, okay, here's X plus Y, Y plus Z has to equal P and Q, okay? Well, this has to be true. This must be the case. This must be the case to be onto. Now we can see that this in fact is a linear system. Again, a slightly different one, because we can see that, well, we're choosing any vectors P and Q. So these are sort of like chosen constants. So we have the augmented matrix for this system. Well, because we want to find X and Y and Z. So what this is the linear system X plus Y equals P and Y plus Z equals Q. Well, so here's the augmented matrix for that. 1, 1, 0, 0, 1, 1, P, and Q. Well, and the question is, we want to be able to find X, Y, and Z. Okay. Well, one way to, we want to find them in terms of P and Q, because that means that no matter what P and Q we choose, we can find the X, Y, Z, the vector in R3 that maps to under this mapping P and Q. So we have to solve this linear system. Well, it's already in echelon form, right? So let's see. But the issue here is that well, there's the leading variables X and Y. So we sort of can think of this as Y plus Z equals Q. So Y equals Q minus Z. Okay. And then we can, because we want to find a form of, here we're going to be able to find it more simply. So we have, okay, then we have the first equation, X plus Y equals P. Then we can use the P here. So we'll have X equals P minus Y, which equals P minus Q minus Z. So we have X equals P minus Q plus Z, and Y equals Q minus Z. And so what we can do is we can always choose Z equals to 0, and then X equals P minus Q and Y equals Q gives you a vector in a vector in R3 that maps to any PQ, because you choose basically, if you want to find PQ, you choose Z equals to 0 and Y equals to Q, and then X equals P minus Q. That's what this says. So because this map is not one-to-one here, it's got many possibilities for the map here. So but basically this shows that F is onto. Okay, and but that's an example where it is onto, we could also find we're also going to be able to check that the map up here, this is onto, but the map G here, the second one's not going to be onto, and let's see how that works. This is G. G is the map from X, Y to X plus Y, Y, and X minus Y. So if we wanted to show that this was, detect what this was onto, we would take this image here, X plus Y, Y, and X minus Y, and set that equal to R, S, and T. Because we can choose, we have to be able to choose an arbitrary vector of R3 and say, is there a vector that comes from this that's on to, can we solve this for any R, S, and T? Okay, so we have a linear system here. Let's write out the equations and see what happens. There's a X plus Z equals R, Y equals S, and X minus Y equals T. Okay, and then we can write the augmented matrix for this. Well, let's go down here and write this as 1, 1, R, 0, 1, S, 1, minus 1, T. Okay, and let's see, this isn't an echelon form, so we can do minus row 1 plus row 3 to get 1, 1, R, 0, 1, S, and then 1 minus 1 plus 1 is 0, minus 1 plus minus 1 is minus 2, and minus R plus T is T minus R. Okay, and then we can do 2 row 2 plus row 3 to deal with this one. So we'll have 1, 1, R, 0, 1, S, and then 2 plus minus 2 is 0, and we'll have T minus R plus 2 times S. Okay, so this is what happens if we go back and look. The third equation here is 0 equals T minus R plus 2S. The problem is that T, R, and S can be anything. So for example, I can choose T equals 1 and R equals S equals 0, and this produces the contradiction. Example, which produces contradiction. Okay, so therefore, because we found we can't choose any R, S, and T and expect X and find an X and Y that maps to it. We can find vectors, in particular this one, in particular this one, 0, 0, 1, that you cannot choose X and Y under this map to find the vector 0, 0, 1. Okay, so that is, so therefore, the map G here, G is not onto. And again, we want to find this is sort of tedious to have to go through this process. So we'd like to be able to detect sort of right away that that maps are like one-to-one and onto. And so that's part of what this chapter is about, is finding easier ways to detect these properties of one to one and onto.